In this video, I'll solve some exercises on the notions that we have already talked about. And it's important that you take your time to understand really, how we are solving them. It's important for the rest of our course. And it would be a really good decision if you decide just before looking at the answer, at my solution, just to try to think of each of these exercises by yourself, even if you don't get to the answer. So, for the first exercise, calculate this big number modulo 7 and this other big number modulo 3. So here we understand for questions that are asked this way, we understand that we should calculate the remainder of the division of these two numbers by the numbers 7 and 3 respectively. So now, of course, it would be, the idea here is not to calculate this number, it's a huge number, but we will use the congruence properties that we already talked about. I'll start by the second one. 2 to the 500 modulo 3. So the answer here should be either 0 or 1 or 2. The first observation I would do is to say that 2 is congruent to negative 1 modulo 3. Why? Because the difference is divisible by 3. The difference is 3 is divisible by 3 without remainder. So 2 to the 500 is congruent to negative 1 to the 500 modulo 3. But now it's very easy to calculate negative 1 or 1 to some power. This is congruent to 1 modulo 3. If I divide by 3, the remainder is 1. Now for the other question, what can we say about 2000 to the power 2000? Modulo 7 this time. The first thing I'll do is just to write here, instead of this one, a number which is smaller. So I find the congruence class of 2000 modulo 7 first. And I do that by dividing 2000 by 7. So if I divide 2000 by 7, I get a 2 here with a remainder of 6, 8 with a remainder of 4, 45, 35 with a remainder of 5. So the remainder is 5. So I can say 2000 is the same thing as 5 modulo 7. When I divide 2000 by 7, the remainder is 5. And by the properties I already know for congruences, if two elements are congruent modulo 7, so when I raise them to some power, they remain congruent modulo 7. But now it's still hard to do because 5 to the power 2000 modulo 7 is complicated to be calculated. I prefer something of the form 1 to the power something or negative 1 to the power something. So what could I do? Here the trick is the following. Calculate the first powers of 5 modulo 7, like 5, 5 square, 5 to the power 3, etc. Modulo 7, until you reach 1. So which is the first power of 5 which is congruent to 1 modulo 7? That's my question. Think about it a little bit. Well, in fact, we have to calculate it. 5 squared is 25, and modulo 7, 25 is the same thing as 4 modulo 7. Now 5 to the power 3 is congruent to, in this equation, I multiply both sides by 5, so it's congruent to 20 modulo 7. And 20 is negative 1 modulo 7. So I know, now if I square both sides, I know that 5 to the power 6 is congruent to negative 1 squared, which is 1 modulo 7. Okay, now how could this help, in fact? How could this help? Well, I know 5 to the power 6 is congruent to 1. The trick is the following now. Divide 2000 by 6 and look for the remainder. So 20 divided by 6 is 3, and I have a remainder of 2. 20 by 6, 3, and I have a remainder of 2, and again 3 with a remainder of 2. The remainder of the whole division is 2. So I can say 2000, the 2000 this time in the exponent, this 2000 is the one that interests me now. is equal to 6 times 333 plus 2. The 2000 to the power 2000 is equal to 5 to the power 2000. But now the 2000 in the exponent, I write it this way. So it's 5 to the power 6 times 333 plus 2. The calculation here everywhere is modulo 7, okay? So I should write perhaps this way. And this is 5 to the power 6 to the power whatever, because this is 1 in fact, times 5 squared. And this is equal to, as we said, this is 1, 5 to the power 6 is 1. So 5 to the 6 to the power whatever is still 1. 5 to the power 2 is 25. And this is equal, or congruent. 25 is the same thing as 4 modulo 7. Because 25 minus 4 is 21, is divisible by 7. And this is my answer, 4. 2000 to the power 2000, if I go and divide by 7, the remainder will be 4. So here you should realize and appreciate the fact that even if these numbers are huge, in fact, computing them modulo the number 7 or 3 turns out to be like, it's easy, we can do it by hand. This problem is easy from a computational point of view, and we'll see later its applications. Following example. Find the units digit of this big number raised to the power 100. So now the first question. What's the relationship between this question and the questions before? How can I frame this in terms of congruence, in terms of the things I spoke about, or we spoke about in this course so far? So think about it a little bit. What does this have to do with the above questions? So in fact, the units digit of a number is the remainder of the division of this number by 10. No? Because we are writing our numbers in decimal representation. Like for the number 23, the 3 here is the number 23 modulo 10. The number 23 divided by 10, you'll have a remainder of 3. So this is the point here. So the question here is, what's this number modulo 10? So again, I do the same thing I've done above. So I say, first of all, the number 1997, etc. is a big number, it's a large number, but I can replace it by its class modulo 10. So 1997 is congruent to 7 modulo 10. The difference, indeed, is divisible by 10. So raised to the power 100 is congruent to 7 raised to the power 100. And now the question, what's 7 raised to the power 100 modulo 10? I do the same trick I've done above. I look for a power of 7 which gives 1 modulo 10. And from there on I continue. So I write 7 to the power 1 is 7, 7 to the power 2 is 49. Now I can continue 7 to the power 3, 7 to the power 4, but I realize that 49 is negative 1 modulo 10. So this is negative 1 modulo 10. And now I can raise both of them to the power 2. So I get 7 to the power 4 is congruent to negative 1 squared, which is 1 modulo 10. But I want 7 to the power 100. So I divide 100 by 4. 100 is 4 times 25 plus a remainder of 0. Here we have a remainder of 0. So 7 to the power 100. I write it 7 to the power 4 times 25 plus 0, which is 7 to the power 4 raised to the power 25 times 7 to the 0. This is 1, so raised to the power 25 it's 1, and this is 1, so this is 1, and all of this is done modulo 10. So 7 to the power 100 is congruent to 1 modulo 10. So this big number we started with is also congruent to 1 modulo 10, which means that when I divide by 10, the remainder is 1, or that its units digit is just 1. So the answer here is 1. Next exercise. So here I have a problem. There's no for all n. Show that this number is divisible by 7. That means it's congruent to 0 modulo 7. So how could I do this here? Let's think a little bit about it. Well, it's a sum of two powers. I've already seen how I can find a power modulo 7. And my trick here is to compute this power modulo 7 and this power modulo 7 and then add the results and see that it's divisible by 7. So for example, if I prove that this is congruent to 3 modulo 7 and this is congruent to 4 modulo 7, so the sum would be congruent to 7 modulo 7, which is then congruent to 0 modulo 7. So the sum is divisible by 7. Okay, let's start. So for the first term of my sum, the first thing I want to calculate 2222 modulo 7. And I do it by just dividing 2222 by 7. When I divide, I get 3 times 7, 21, remainder 1, 12, 1 times 7, 7, remainder 5, 52, 7 times 7, 49, and I have a remainder of 3. So this is 3 modulo 7. So I can say that 2222 to the power 5555 is the same thing as 3 to the power 5555 modulo 7. Okay, and now it's getting simplified, but it's not enough. I want to compute that modulo 7 and find a number between 0 and 6. So as above, I search for the first power of 3, which gives me 1 modulo 7. So I compute it. So 3 to the power 1 is 3. 3 squared is 9, which is 2 modulo 7. 3 to the power 3. So I multiply both sides by 3. Here I have 3 to the power 3. And on the other side I have 3 times 2, which is 6, which is negative 1 modulo 7. Okay, I reach negative 1. Now I can continue by multiplying by 3, or I just realized that I can square both sides and get 3 to the power 6 is 1 modulo 7. Okay, good. Now I'm raising 3 to the power 5555, and I know 3 to the 6 is 1. So I want to write this number, the exponent, as something times 6 plus some remainder. So I divide 5555 by 6, 55 9 times 6 remainder 1, 15 2 times 6, 12 remainder 3, 35, I get to 30, and remainder of 5. So I can write 5555 is 6 times 925 plus 5. So 2222 to the power 5555, we showed it's the same thing as 3 to the power 5555. But this in turn, the 5555, I write it using this expression. So it's 3 to the power 6 times 925 plus 5, which is 3 to the 6 to the power whatever, times 3 to the 5. But 3 to the 6 is 1, so 3 to the 6 to the power whatever is still 1, and the whole thing is 3 to the power 5. Now 3 to the power 5 can be very easily calculated, modulo 7, so I can write it, I don't know, 3 to the 2 times 3 to the power 2 times 3 which is 3 to the 2 is 2 modulo 7, and the other 3 to the 2 is another 2 modulo 7 times 3. So it's 12, and this is 5. 12 is 5. All of this is done, of course, modulo 7. These equalities are true modulo 7. Okay, so the number I started with is congruent to 5 modulo 7. So I write it here, 2 to the power 5, 5, 5, 5 is congruent to 5 modulo 7. So great, this first term is just 5 modulo 7, so I have to show that this is 2 modulo 7. And so the sum would be 7 modulo 7, which is 0 modulo 7, so it's divisible by 7. It's just exactly the same thing as above, so I just invite you to try to do it by yourself. I'll go a little bit quickly on this one. So when I divide this number by 7, I have a remainder of 4. And now when I start calculating the powers of 4, so 4 squared is 16, which is 2 modulo 7. And 4 to the power 3 is 4 times 2 is 1 modulo 7. Great, I quickly reached the 1. And now, as above, I have to find the remainder of the division of this number, 2222, by 3. So when I do the division, I have a remainder of 2. And I can write that 2222 is 3 times 740 plus 2. So the number 5555 to the power 2222 is equal modulo 7, or congruent modulo 7, to 4 to the power 2222. And using this here, I write it 4 to the power 3 to the power 740 times 4 to the 2. But 4 to the 3 is 1 modulo 7, so all this is 1 modulo 7. And this is 4 to the 2, it's 16, which is 2 modulo 7. So this is 2 modulo 7. Okay, so here I can write 2. So in my sum, the first term is congruent to 5 modulo 7, the second is congruent to 2 modulo 7, so the sum is congruent to 5 plus 2 modulo 7, so 7 modulo 7, which is 0 modulo 7. And a number congruent to 0 modulo 7 is divisible by 7, and that's what we want. Next exercise, show that for our natural number n, 5n to the power 3 plus n is divisible by 6. How can we do it? This time we have to show something for every natural number n. In fact, the congruence class of this number will depend only on the congruence class of n. So we'll study the possible cases for the congruence class of n modulo 6, and there are only 6 of those. So I'll make a small table. So here n could be 0, 1, 2, 3, 4, and 5 modulo 6. N to the power 3 is if n is congruent to 0, n to the power 3 is congruent to 0 to the power 3, which is 0, modulo 6. If n is congruent to 1, n to the 3 is 1. If n is 2, n to the 3 is 2 times 2 times 2, which is 8, which is 2, modulo 6. If n is congruent to 3 modulo 6, so n to the power 3 is congruent to 3 to the power 3, but 3 to the power 3 is 27, which is 24 plus 3, so it's the same thing as 3 modulo 6. If n is congruent to 4, n to the 3 is congruent to 4 to the 3, but 4 to the 3 is 64, let's say, and modulo 6, it's 4. Last case, if n is congruent to 5, modulo 6, so n to the 3 is 5 to the 3, Now I know I can calculate 5 to 3 is 125, which is 120 plus 5, and this is 0 modulo 6. The whole thing is 5 modulo 6. I'm just using the basic fact that if A is congruent to B modulo whatever, and A prime is congruent to B prime modulo n, then A times A prime is congruent to B times B prime. And here I'm taking, in this case, A equals A prime, so I can say A square is congruent to B square. And then multiply one other time by A and have A cubed congruent to B cubed if A is congruent to B. This is called the compatibility of the congruence relation with the multiplication. And it's also compatible with the sum. We'll use it just now. If A is congruent to B and A prime congruent to B prime, I can also say that A plus A prime is congruent to B plus B prime. Anyway, I'm not interested in n3, I'm interested in 5 times n3. So 5 times n3 is congruent. In the first case, it's 5 times 0, which is 0. In the second case, it's 5 times 1, which is 5. Then 5 times 2, it's 10, but 10 is 4 modulo 6. Then 5 times 3 is 15, which is 3 modulo 6. Then 5 times 4, it's 20, which is 2 modulo 6. And 5 times 5 is 1 modulo 6. And now I want 5n3 plus n. 5n3 plus n is congruent to what modulo 6? In the case where n is congruent to 0 modulo 6, 5 and 3 is also congruent to 0 modulo 6. So 5 and 3 plus n is congruent to 0 plus 0, which is 0 modulo 6. If n is congruent to 1 modulo 6, then 5 and 3 is congruent to 5 modulo 6, and the sum is congruent to 1 plus 5, which is 6 modulo 6, which is 0 modulo 6. If n is congruent to 2, 5 and 3 is congruent to 4, the sum is congruent to 6, which is 0, and this is the case for all of them. So in any case, 5 and 3 plus n is congruent to 0 modulo 6. So 5 and 3 plus n is always divisible by 6. Now, show that modulo 3, any number is congruent to the sum of its digits. Now there's this test for divisibility by 3, which you probably know. If I take a large number, let's say 2, 1, 3, 5, 7, and I want to see if it's divisible by 3, I can just add its digits. 9 plus 1 is 10, plus 3, 13, plus 5, 18, plus 7, 25. And 25 is not divisible by 3. So the original number is not divisible by 3. In fact, I can go further. I can say, what's the remainder of the division of 25 by 3? I know that 25 is 3 times 8 plus 1. So the remainder of the division of this one by 3 is 1. So the original one, if I divide by 3, the remainder is 1. So this is the criterion, this is the divisibility rule. But why does it work? Now the important thing here, we are taking the sum of the digits of the decimal representation of the number. So the number, we are writing it in base 10. And in this base, in this representation, we are summing the digits. If you are representing it in base 2, it doesn't work. So why is this true? Suppose I have a number, let's say its decimal representation is a n minus 1, a n minus 2, etc. till a0. What does this mean? Let's call this number x. What does this mean for x? It means that x is equal to a0 plus 10a1 plus 10 squared a2 plus etc. until 10 to the power n times an. Is this true? We can just think about it a little bit. Let's see. I'll take an example. Suppose that x, the decimal representation of x is, x is 3,422. And I'm writing it in its decimal representation. I understand by this is that x is 3000, like I'm saying it's 3400, it's like 3 times 1000 plus 4 times 100, which is 10 to the 2, plus 20, like 2 times 10, plus 2. That's what I mean by decimal representation. That's what I understand. Those are the powers of 10 which appear here. And holds for any x. Now what we are saying is that x is congruent to a0 plus a1 plus a2 until an. Is this true? Let's see. 10, the 10 here is congruent to 1 modulo 3. So 10 squared is congruent to 1 squared, which is 1 modulo 3. So this is 1 modulo 3. And 10 to the power n is congruent to 1 to the power n, which is still 1 modulo 3. So all of the powers of 10 are congruent to 1 modulo 3. So this equality here, if I take it modulo 3, all the powers of 10 I can put instead of them 1. And so I get the criterion. I get that the number x is congruent to the sum of the digits of its decimal representation, modulo 3. Which in particular means that if I divide x by 3, or if I divide the sum of its digits by 3, I have the same remainder. And in particular, the remainder is 0 in the first one if it's 0 in the second one. So the number x is divisible by 3 if and only if the sum of the digits is divisible by 3. And that's the rule for divisibility by 3. Well, let's check it on a small number. Let's say, I don't know, 25. I know that it's not divisible by 3, but it's the remainder when I divide by 3 is 1, because 25 is 24 plus 1. Now, if I take the sum of the digits here, it's 7. And also the 7 when I divide by 3, I get a remainder of 1. The same thing. Next exercise. So find divisibility rules for 9 and 11. For 9, it's just the same one as for 3. Because 10 is congruent to 1 modulo 9, 10 squared is congruent to 1 modulo 9, etc. And it's the same, just the same argument which applies to 3, it applies to 9. A number is divisible by 9 if and only if the sum of the digits of its decimal representation is divisible by 9. Now for 11. 11 is interesting. We want to apply the same method as before, but we want to know that the powers of 10 are congruent to what modulo 11? 10 itself, well, is congruent to 10, but I can say also it's congruent to negative 1 modulo 11. We like 1 and negative 1 in congruences. Now 10 squared is congruent to negative 1 squared, which is 1 modulo 11. 10 to the power 3 is congruent to negative 1 to the power 3, which is negative 1 modulo 11. And 10 to the 4 is congruent to 1 modulo 11, and so on and so forth. Okay, now I take an x which has this decimal representation. The units digits is a0, then a1, a2, until an. It's the decimal representation, and this means exactly that the number x is 10 to the n times an plus 10 to the n minus 1 times an minus 1, and so on and so forth, until I get to the 10 squared a2 plus 10 a1 plus a0. And now 10 is negative 1 modulo 11. 10 squared is 1 modulo 11, and 10 to the power 3 is negative 1, and so on and so forth. So what's 10 to the power n modulo 11? Well, if 10 is negative 1, then 10 to the power n is negative 1 to the power n. So when I reduce this modulo 11, x will be congruent to a0 minus a1 plus a2 minus a3, etc. The last term is negative 1 to the power n a n. So here you don't take the sum of the digits, you take just the alternating sum. And the number is divisible by 11 if and only if this alternating sum is divisible by 11. And moreover, the remainder of the division of x by 11 is the same as that of that alternating sum by 11. If we take a small example, let's say, I don't know, 121. I know that 121 is divisible by 11. It's 11 times 11. If I take the alternating sum, I have to take 1 minus 2 plus 1. Donc is congruent to 1 minus 2 plus 1, which is congruent to 0 modulo 11. So it is divisible by 11. Yeah, I know it. Okay. But it's interesting to realize that if you take, if your number has 2 digits, it is divisible by 11 if and only if these 2 digits are equal. We know that, in fact. Like 66 is divisible by 11. And indeed, it's congruent to this 6 minus this 6, which is congruent to 0 modulo 11. Now, if I take a randomly chosen number a little bit bigger, 2, 3, 1, 0, 0, 1, 3, 9. So this is congruent to modulo 11. This is congruent to 9 minus 3 plus 1 minus 0 plus 0 minus 1 plus 3 minus 2. It's congruent to 7 modulo 11. 7 is between 0 and 10. So this number, if I divide by 11, the remainder is 7. And in fact, even if you get a small number, a negative number, the criterion, the rule still works. Like if I take this example, 9, 1, 2, 1, this one, this is congruent to 1 minus 2 plus 1 minus 9, which is congruent to negative 9 modulo 11. So it's not 0 modulo 11. So it's not divisible by 11. And the remainder of its division by 11 is the same as the remainder of the division of this one by 11. So here I can add 11 and I get 2 modulo 11. So this number, if I divide by 11, I get a remainder of 2.